All right. Looks like there's only 3 of you today. I hope you had a good break. And for the last week of class, we're going to be doing as much as we can about the structure of the standard model of particle physics. And so what we're going to start with today is spontaneous symmetry breaking. And so I'll be talking about this from the point of view, not of the standard model, but a toy model. And then once we see how it works for the toy model, it will hopefully be clearer how it works for the standard model. So the idea here for spontaneous symmetry breaking is that the laws of physics are invariant under a symmetry of some kind, but the ground state of the universe, the ground state that we live in, is not. So just as an example, Maxwell's equations that describe electromagnetism are invariant under Lorentz transformations, unknown to Maxwell, but it's true anyway. And so one consequence of that is that there is no special direction. And yet it might be true that we live in a state that does have a special direction. For example, the ground state of a ferromagnet. We could imagine that our entire universe is inside of a giant ferromagnet, or consists of a giant ferromagnet. There's iron everywhere, and it has some non-zero magnetization. Remember, magnetization is the dipole moment for unit volume. And so you could be living in a state where at every point there's some magnetization, all pointing in the same direction. And that would break the Lorentz symmetry because there is a special direction associated with it. So that's just one example of how spontaneous symmetry breaking could occur. There are two general types of symmetries that we might be talking about, and we'll talk about both of them. Okay, so one is global symmetries, which means that whatever symmetry transformation you're doing, it's the same at all points. So a transformation, same at all points. And then there are local symmetries where the transformations can be different at all points. So we're going to start with the case of a global symmetry. And in fact, it's going to be a U1, therefore abelian global symmetry group. So to give an example of a theory that has such a symmetry, let's consider a complex scalar field, which I'm going to call phi. So phi depends on position in four-dimensional spacetime. And we know how to write down a Lagrangian for such a theory. That's Lorentz invariant. So one way is partial mu phi star, partial mu phi. That's our kinetic term. And then I could just write any potential that's a function of phi and phi star. So for example, I might write my potential like this, that it's equal to m squared. M squared is just some number that has units of mass squared times phi star phi plus lambda times phi star phi squared. So I'm only including those combinations in order to make sure that my theory actually has a symmetry. In fact, my theory is invariant under the following transformation. If I take phi and I replace it by, let me call it phi prime, prime does not mean derivative here. Phi prime is e to the I alpha phi, where alpha is any constant. And it's important that it's a constant. That's what makes this a global symmetry, as opposed to something that you could say alpha may depend on position as well. All right, so now if I have this Lagrangian, I can write down the equations of motion. And if you take the variation of the Lagrangian with respect to phi star, you find out the equations of motion look like this. Partial mu phi plus the derivative of phi with respect to with respect to phi star, that has to equal 0. All right, so we'd like to find solutions to this equation of motion. The solutions to the equation of motion will correspond to the theory in the vacuum state. So one solution that's might be kind of obvious is you could say that phi is some constant that minimizes the potential. Okay, and the reason that's a solution is because if it's a constant, the first term is taking derivatives of it, so that's just 0. And if it minimizes the potential, that means the derivative of the potential has to be 0 at a minimum. Okay, and so that will work. And now we need to split this up into different possibilities for what m squared and lambda are. So here's one possibility, is what if m squared is greater than 0 and lambda is greater than 0? Then if I graph the potential as a function of phi, right, it's just going to look like that. It's got a minimum at phi equals 0. And so my solution to the equations of motion is just phi equals 0, not very exciting. And the quantum mechanical version of this is saying that the ground state if I compute the expectation value of the field operator is just 0. So that's characterizing the ground state, and then scalar particles as opposed to scalar fields. Scalar particles are oscillations, quantized oscillations about the minimum. All right, so that's one possibility. Another possibility is if m squared is greater than 0 and lambda is less than 0, then what does this thing look like? This is the potential as a function of phi. And so now what it'll look like is something like this. At large phi, lambda takes over, and the potential goes off to negative infinity. And so this is unstable. And this is presumably not an acceptable theory. So we just can't live in a universe that has that Lagrangian. And in fact, if you think about it, the m squared greater than 0 part of this doesn't really matter. If m squared was less than 0, it would just be even worse. It would just go off to infinity, negative infinity like that. Okay, so a third possibility though is, what if m squared is less than 0 and lambda is greater than 0? So you might say, well, wait, how can you have m squared less than 0? That would make m imaginary, but really m squared is just the number in the Lagrangian. It's not really the square of any number m. There's not really a number m that one should talk about separately. There's just m squared. So now if I graph v of x, or sorry, v of phi versus phi, it's going to look something like this. Okay, near the origin, m squared is the important term, and that goes negative. But then for larger phi, the positive lambda takes over, and the potential looks something like that. And so there will be a minimum value. And you can even minimize the potential to find out the minimum value of phi squared is going to be v squared over 2, where v is the square root of minus m squared. Remember, that's a positive number divided by lambda, which is another positive number. Okay, and then the quantum mechanical version of this is that the expectation value of the field in the ground state is v over, basically the minimum value of phi, v over square root of 2. This is called a vacuum expectation value for the field, or usually we just write VEV for VEV, vacuum expectation value. So the reason this is referred to as spontaneous symmetry breaking is, let's say you take this matrix element, this expectation value, and now perform a U1 transformation, our symmetry transformation. How does it behave? So now we're calculating phi prime of x, and that's just e to the I alpha times the thing before the transformation, which is e to the I alpha v over square root of 2, which is not the same thing as v over square root of 2. Unless, of course, v was 0. That's this case way back up here. Okay, so as long as v is not 0, our vacuum state is not invariant under the symmetry, even though the Lagrangian that gave rise to it was invariant. So I should say under the symmetry. All right, so now let's think about what this means from the point of view of the particles and interactions of the theory. And to do that, we're going to consider fluctuations around this vacuum. So consider fluctuations around the vacuum expectation value. We're actually going to do this in two slightly different ways that have will help us understand the theory in two different ways. So one way is to just take our field and write 1 over square root of 2, that's just a convention, times the vacuum expectation value plus a real field that I'm going to call capital R, plus I times another real field that I'm going to call I. Okay, so R and I here are both real fields. And what I've done is I've just expanded my general complex field as a real part plus an imaginary part but also separating out the vacuum expectation value part. Okay, and then I can do the complex conjugate of that. We're assuming that V is real. And so all I get from the complex conjugate part is that the coefficient of the real field I of x gets a minus sign. All right, and so now the strategy is to take those equations and plug them into our Lagrangian and see what the Lagrangian becomes in terms of R and I. So first of all, there's the kinetic term, which looked like this. And when you plug in that, the V's go away because you're taking derivatives acting on them. And all that's left is just what you might expect. Namely, you get kinetic terms for each of R and I. These are normal kinetic terms. And notice there's a factor of 1/2 because real fields have a 1/2 in their kinetic term, whereas the complex fields don't. That's why there's a 1/√2 in front of these. Okay, and then there's, if you write down the Lagrangian, actually minus the Lagrangian, contains the potential. And so now if you just take these expressions and plug them into the potential, you will find the following. There's lambda v squared times r squared plus lambda vr times r squared plus I squared plus lambda over 4 r squared plus I squared squared. So the original Lagrangian, if we go back up here somewhere, the original Lagrangian had an m squared, but what I've done is I've replaced that m squared using this equation to write everything in terms of v and lambda. Okay, so that's what's been done here to simplify this. And notice that what we've got there is we've got a field squared terms, which makes it a mass squared term. And we've got a term with fields cubed, r times r squared and r times I squared. And that's an interaction. And then we've got things that have fields, 4 fields. So I can write that schematically as field to the 4th power. So we've got a mass squared term, but we've also got terms that look like this. If I draw, let me use a different color for the terms in the Feynman rules. I've got things like R, 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 and R, I. And here in the last term, I've got terms like R, 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 and R, R, I, and I. So I'm not going to write out the Feynman rules exactly, but those are just the sorts of terms that appear in the Feynman rules from this Lagrangian. Okay, so those are the interactions, and we can also read off that the R field has a mass that is equal to 2 lambda v squared. That's just what this term is. But notice there is no term with I squared. So m of I squared is 0. In other words, what we found is that by having a spontaneous symmetry breaking, we get automatically a massless field. That's the I field. Okay, so this is a very deep truth that when you break a symmetry spontaneously, you get a massless field. It's so important that we're going to redo it a different way now. This has the same physical content, but it's going to look different. So our different way this time is, instead of expanding our field in a real and imaginary part, I'm going to expand it as a real part times a complex phase. Okay, so phi of x equals 1 over the square root of 2. V plus, I'm going to call this field H. H is secretly for Higgs. So that H is a real field, and now I'm going to multiply by a complex phase, which I'm going to call G for Goldstone. To make it dimensionless in the exponential, I'm going to divide by the vacuum expectation value. And so H of x and G of x are real scalars. They're real scalar fields. Okay, so I can always do that. I can take a general complex field and write it as a real part times a complex phase. I've done it in such a way that I've separated out the vacuum expectation value. Okay, and so now phi of x star, I just take the complex conjugate. That part doesn't change, but the exponential, of course, changes because I took the complex conjugate. And so now if you plug that into the potential, again, all of this is just a different way of analyzing the same theory. It's not a different theory. Now we get lambda v squared h squared plus lambda v h cubed plus lambda over the fourth, lambda over 4 h to the fourth. So one interesting thing that happened here is that there's no g of x at all in this potential. Okay, so the g of x in this way of doing things just doesn't appear. But there's also the kinetic term of the Lagrangian. Let's see what that is. When you plug in these phi and phi star, you get 1/2 partial mu h partial mu h. That's a normal kinetic term. And the rest of it works out to be 1/2 1 plus h over v squared partial mu g partial mu g. Okay, so the g field does appear, but only with derivatives acting on it. Okay, there's also quadratic. So we can combine this term in the Lagrangian with these terms in the Lagrangian that have only two fields. Notice this one has a field there and another field there and another field there, but the one part doesn't have any extra field. So the quadratic part of the Lagrangian just looks like this. 1/2 partial mu h partial mu h plus 1/2 partial mu g partial mu g minus 1/2 mh squared h squared. And that's the part of the Lagrangian, because it's quadratic, that's going to give us our propagators. Notice that once again, it's telling us there is one massive field and one massless field. Okay, and this mass squared here is in fact the same as this mass squared. So it's really talking about the same theory in a different, slightly different way. But now we can write the interactions. The interactions are everything that's not quadratic in the fields, and so you just gather everything up. And it looks like this. There's an h cubed term, there's an h to the fourth term, and then there are some terms with extra terms with derivatives. Okay, we can't put this in the propagator because it's got 3 fields in it. Propagators only have 2 fields. And then plus 1 over 2v squared, h squared, partial mu g, partial mu g. Okay, so what have we learned by doing it this way? G is, it's known as a Goldstone boson or a Nambu Goldstone boson. Okay, and it's massless. Only H had a mass term. And not only is it massless, but if you look at all the terms in the Lagrangian, it only has derivative interactions. So the only interactions it has derivatives acting on it. So only has interactions with derivatives. And so in a sense, this is a more interesting way than the first way we analyzed this, because we've learned that in this way of writing the fields, there's this nice fact that we'll never get an interaction that has G without a derivative acting on it. All right, so there's a general summary of all of this called Goldstone's theorem. We did this for a single abelian symmetry, but the general Goldstone's theorem applies to even non-abelian invariances, and it says each spontaneously broken global symmetry, and it's very important that it's global, gives you a massless Nambu Goldstone boson. Okay, so we're not going to prove the more general thing, but it's actually not even that hard, but it would take us a little while. All right, any questions on that so far and how Goldstone's theorem works for global symmetries?
Professor, so I might have missed it, but before, were we taking mass to be negative, like
Yes.
in the first? So why was that though?
So it's just a choice that we can make if we're choosing our theory. So if m squared was positive, then you would just get this situation. That would be perfectly fine, but it's just sort of boring, right? So we're just choosing to consider what happens if m squared is less than 0, just because it's an interesting case. And it just so happens that in the standard model, that's what seems to be true.
But isn't it like unphysical? I mean,
no, it actually turns out it's perfectly physical. It might seem a little bit strange, but there's actually nothing wrong with it. So if m squared is less than 0, it just means that you should not be expanding your theory, fluctuations in your theory around this point. That's a bad point to expand your theory around. And instead, the lesson is that you should be expanding around this point. If you expand around this point, then you find out the actual physical masses of particles are given by 0 for one of the masses and a positive mh squared for the other mass. So maybe I should write that down, that here mh squared is actually 2 lambda v squared, which is positive. Okay, so maybe another way of saying it is that in spontaneous symmetry breaking, you have to expand around the right point in field space in order to see that your theory makes sense. Does that make sense?
Yeah, it does.
Okay, any other questions before we move on to local symmetry breaking? Okay, so local symmetry breaking, otherwise known as the Higgs mechanism, okay, has the this applies to gauge symmetries. And so that's what's going to actually happen in the standard model. But we're not going to do the most general today. We're not going to do the most general case. We're going to just again consider a U1 gauge symmetry. Many of the things I'm about to say will also apply to non-abelian. We'll see how that works in the next lecture. But let's say, for example, you have some fermion field and it transforms like this. E to the IQ, Q is the charge, theta x, psi of x. So Q is the charge, and theta of x is a gauge parameter which depends on position now. And so that's what's making it a local symmetry. All right, so now if I have a theory that has this symmetry, and then psi bar of x goes to e to the minus IQ theta of x, psi bar of x, then one thing we found is that you then have to introduce a gauge field, which is a vector, which I'm going to call a mu of x, whose transformation looks like this. Okay, notice it transforms proportional or with a term that has the derivative of theta in it. That's why it's important that theta can depend on position. Okay, and G is the gauge coupling, which then appears in the Lagrangian. The way it appears is that you're then forced, in order to make this be a symmetry of the Lagrangian, you're forced to introduce a covariant derivative for your fermions. In this case, I'm just assuming there's just one fermion. So the covariant derivative, capital D mu psi, is the ordinary derivative plus I times the charge times the gauge coupling times the vector field, all multiplying or acting on psi. Okay, now in order to have symmetry breaking work, I also want a complex scalar field, just like in the global case. So we're also going to put in a complex scalar field. We'll again call it phi, and I'm going to call it charge 1, which isn't actually necessary. But if you think about it, if the charge isn't 1, then I can redefine all of my charges to make it be 1 if I wanted to. Okay, and so what that means is that phi of x transforms under the symmetry into e to the I theta of x, phi of x. Okay, and phi star, of course, transforms in the opposite way. Okay, if the charge wasn't 1, I would just be putting some extra factor in the exponential. Okay, and going along with that, there are covariant derivatives for the scalar fields. So d mu phi is partial mu phi plus I g a mu phi, and similarly for the complex conjugate. These are the building blocks for derivatives that one can use to construct a Lagrangian that's invariant under the symmetry, as well as the Lorentz symmetry, which we also need. So in fact, I can write down a Lagrangian right now using these building blocks. So I'm using the covariant derivatives rather than ordinary derivatives. And then I also have a potential that depends on phi and phi star. And I need a kinetic term for my vector field. which looks just like it does for quantum electrodynamics. And then there are the terms for the fermions that I'm not going to bother writing because they're not going to be very important for what we assume. Okay, and as before, we're going to assume the same sort of potential. So our V is an m squared term, that's going to be negative. Phi star phi, and a lambda term, phi star phi squared. And we're going to choose, we have the 50-50 chance, so we're going to assume that m squared is less than 0. And then exactly the same way as before, the expectation value of phi, the vacuum expectation value, is some number that we're going to call v over square root of 2, which is square root of minus m squared over 2 lambda. Okay, so a lot of this is going to look like the same stuff. In particular, we're now going to follow our second method and decompose phi of x into real fields, h and g, as before. Okay, so phi of x is going to equal 1 over square root of 2, v plus h of x times e to the I g of x over v. Okay, and so let's plug that in. One thing we're going to need is the covariant derivative for phi. Okay, and that, when you plug it in, looks like the following. E to the I g over v. All right, and so now I could do the same thing with d mu phi star, but I don't think I'm going to write it down. All you do is, for that, is you take g and replace it by minus g. And so notice that this term right here is just going to have the opposite phase. And so this exponential is just going to cancel and leave behind the rest of this stuff. And it's going to be useful to define this combination of fields as a new vector field. And let's call it v mu for vector. All right, so I'm just redefining my vector field. V mu is just this linear combination, which appears in this nice way. And a nice thing about that is, let's say I do the same thing. Let's say I consider f mu nu. Right, remember f mu nu is partial mu a nu minus partial nu a mu, which turns out to be exactly the same thing in terms of v. So it's partial mu v nu minus partial nu v mu. And the essential reason for that is, if you think about this extra term, it's going to have partial mu minus partial mu, both acting on g, and partial derivatives commute. So that's why this is really just the same thing as that. Okay, so I can write what's gone on here as d mu phi equals 1 over square root of 2 partial mu h plus I g v mu v plus h times this phase, and then for d mu phi star, okay, it looks almost the same, except the imaginary term, of course, gets complex conjugated, and the phase gets a different sign. Okay, so as I mentioned before, when I multiply these together, this and this are just going to cancel and give 1. And so when you plug all of this into the Lagrangian, here's the final result. The Lagrangian is 1/2 partial mu h plus g squared v plus h squared v mu. Okay, so the cross terms here cancel because they have the opposite sign, and the plus I and the minus I gives the g squared with multiplying by the g, and so that's what you get. The f mu nu term stays the same. And then finally, there are some terms from the scalar potential which organize themselves into the following, or can be organized into the following. Okay, so what have we got here? A very interesting thing has happened, which is the would-be Goldstone boson has disappeared. It's just gone. So the would-be, and this is actually what it's called, the would-be Goldstone boson, G of X, has disappeared. It's not part of the theory anymore. So what happened to it? What happened to it was we chose a new vector field which absorbed into it what used to be the Goldstone boson, or what was trying to be the Goldstone boson. Notice it's also gone from the scalar potential. It's just completely gone. And now you can read off the Higgs mass, the mass of the H field. Namely, mh squared is 2 lambda v squared. All that comes from is when I expand this out, there's one term with h squared in it, and that's its coefficient. Okay, so the Goldstone boson in a local symmetry went away. We got a positive Higgs mass squared. And the other thing that happened is for the vector fields, okay, the Lagrangian with 2 vector fields has the usual QED part, the f mu nu, plus g squared v squared over 2 v mu, which is a mass term for the new vector field. And in fact, now we can read off what it is. mv squared is g squared v squared. All right, so the words that one attaches to what's going on here is the vector got a mass by eating, in quotes, the Goldstone boson. For many years, the Physical Review would not accept your paper if you said it ate the Goldstone boson. They would insist that you say it absorbed the Goldstone boson, but I think they finally allow you to say that it ate the Goldstone boson. In any case, people usually say it eats the Goldstone boson. And so your massless, or your would-be massless A mu, which had 2 degrees of freedom, because massless gauge particles, massless vector particles, have only transverse degrees of freedom. There are 2 polarizations for the photon, has become a massive V mu, which has 3 degrees of freedom, because it's not massless anymore. It's 2 transverse and 1 longitudinal, which you can't have, for example, for a massless photon. Massless photons don't have longitudinal degrees of freedom or longitudinal polarizations, but massive ones do. Okay, so that's what happened to the goldstone. It became the longitudinal degree of freedom for the massive vector field, and you now have left over a single real field, which is the Higgs boson. This is the Higgs boson for this toy model. When we do this next time for the standard model, we're going to find out that exactly the same thing happens, even though it's a different symmetry that gets broken. Okay, any questions on that so far? All right, so yet another way of interpreting this in words. I mean, the equations don't lie. You can just sort of write down the Lagrangian and pick out what are the terms that are left over after you've done all this stuff. But another way of saying what's happened is that the goldstone has been gauged away. Okay, there's different words. We can say it got eaten by the vector, or we can say it got gauged away. So recall that we had written the scalar field like this. Right, but when you write it that way, you realize that e to the I g over v is just a complex phase, and that's exactly what the gauge transformation does. It multiplies by a complex phase. So under a gauge transformation, you can take phi goes to e to the I theta times phi and use that freedom to choose theta of x. Since it depends on position, you can just choose it to be equal to minus the field g of x divided by v. Nothing can stop you from doing that because of the fact that your symmetry theta, that parameter can depend on position. You can just choose it to be equal to minus the field divided by the v. This is known as going to unitarity gauge. That's just the name of this particular gauge where you choose theta in that way. Okay, and in that gauge, now you understand why there's no g anymore, because phi is just equal to 1 over square root of 2 v plus h of x. Okay, so that was why it was sort of inevitable that there had to be a way of writing the theory in such a way that g did not appear. Okay, so v mu, in this way of saying things, is the unitarity gauge version of a mu. All right, so we can summarize this by saying, okay, in terms of v mu and h, what are all the Feynman rules? Let me just sketch them out, just for the record. So one thing is you have this massive vector. The Feynman rule for its propagator looks like this. I over p squared, let's say the momentum is p squared minus mv squared. We've actually seen this before when we talked about the weak interactions, because that's in fact what this is. So there's its Feynman rule, but I should emphasize this is in unitarity gauge. It's different in other gauges. And you can look up what the propagator looks like in other gauges. Okay, but in principle, all you need is one gauge in order to do calculations. The Higgs boson, okay, gets a Feynman rule. That's the usual thing for a scalar field with a mass. Okay, and then there are terms in the Lagrangian which couple a Higgs to two V's. So for each V, I need a vector index. And the Feynman rule for this is 2I G squared V G mu nu. This is this is a striking thing that only occurs in spontaneous breaking of theories. In other words, you normally don't expect there to be an interaction with a single scalar and two vectors. But in spontaneous breaking, it does occur. We can see where that came from by going back to the Lagrangian up here. It's expanding this. So there's one V times one H times two vectors. Okay, that's where that comes from. There is similarly a Feynman rule that has two H's. In the real world, this one's very hard to see. Okay, and this one looks like 2I G squared V squared, G mu nu. But there is also, if you go back here, oops. If you go back here and expand that, there's an H cubed term and H to the fourth term. And the H cubed term looks like this. Oops. For which the Feynman rule is minus 6I lambda V, and the H to the fourth. There's a Feynman rule that has four H's, and the Feynman rule for that is minus 6I lambda. And then for the fermions, which I haven't bothered writing down because really nothing particularly interesting happens in that part of the Lagrangian. But I just have for each fermion, I can interact with the V field, and the Feynman rule like for that is just minus I times the gauge coupling times the charge times gamma mu. And that's as before. All right, so all of that was for our toy theory that only had a U1 symmetry. And what we will do next time is talk about how this works in general. I won't be deriving it in exactly the same way. I'll just be writing down the answers. And then we'll apply that to the particular case of the standard model. All right, any questions on that?
Yeah, going back to when we choose theta of x equals to the minus g of x over v. So we choose the unitarity gauge, right?
Yes.
This is, so that's for a local symmetry, right? So what's to say that that doesn't change to, so I guess the x dependence on theta is buried in the Goldstone. The Goldstone's dependent on x, right?
So I think the way to say it is in both theories, the local and the global case, in both theories, you had a g of x.
Mm-hmm.
But if you want to get rid of it by doing a gauge transformation, you have to get rid of it everywhere for all values of x. And since g of x can be different for different values of g of x, that means you have to have a local symmetry so that you can choose your theta to exactly cancel it at every value of x.
Right.
So that's why it doesn't work for global symmetries.
Gotcha. Okay.
Okay. Was that your question or was I?
Yeah, no, that helps. Thanks.
All right, other questions? So next lecture is again going to be on Zoom, but the last lecture of the semester on Friday will be in person again. So I'll send you an email reminder of that. And then you have homework due. And then I think I'm going to, as I mentioned before, I think I'm going to make a short-ish homework set that will be due on the last possible day, which I still haven't figured out when that is, in finals week. All right, so if there are no other questions, I will see you on Wednesday on Zoom.
All right, thanks.
All right, have a good day.
Professor, where can we find the videos for the 686?
Oh, right. Sorry. Yeah. So I might be able to put them on. My advice though would be to, instead of looking for the videos, to read the notes, because it should
Oh.
correspond to exactly what's in the notes. And I think the notes are better than the videos. So, did you miss one? Did you miss a lecture? Is that why you're asking? Or,
No, so I thought they'll be up on YouTube because the 660 ones are there.